Imagine a scenario that plays out in, well, almost every major enterprise today. You hire an elite red team, right?
Right. The brilliant, highly paid, ethical hackers.
Exactly. You hire them to test your defenses. So they sit down with their energy drinks, they fire up their laptops, and for the next 3 weeks, they just meticulously map your network.
Pinging everything.
Yeah. They probe your firewalls, they hunt for, a misconfigured server, and finally they write a beautiful custom exploit to breach your system.
And then comes the 50-page PDF report.
The massive PDF. And you read it, you feel secure, and you patch the hole. But here is the terrifying reality we're actually facing today. While that human team spent 3 weeks finding a single attack path.
An autonomous AI swarm could have done it in seconds.
Right. It could have mapped that exact same network, built a mathematical replica of it, hallucinated like 10,000 variations of your infrastructure, and compromised it from 100 different angles.
All before the human hackers even finished their first cup of coffee.
Exactly. I mean, we are standing at the edge of a fundamental paradigm shift in digital defense.
We really are. It's a complete inversion of how we think about time and scale in cybersecurity. We're moving from a world where security is an event, like a scheduled test,
Right.
to a world where it's a continuous living, breathing process.
And that living process is the entire focus of today's deep dive. We are unpacking a massive stack of cutting-edge research centered around something called the real-to-sim-to-real pipeline.
It's a fascinating framework.
It really is. It's a revolutionary framework that is actively teaching artificial intelligence to autonomously hack networks. The goal here is for enterprise security teams to deploy these AI agents to find and patch vulnerabilities before real, malicious actors can exploit them.
And they will exploit them.
Oh, absolutely.
Yeah.
But before we get into the incredibly dense mechanics of how an AI actually learns to hack, I really need to send a massive thank you to our sponsor, CISOmarketplace.com.
Essential resource right now.
Honestly, yes. If you are managing an enterprise network and you're listening to what we're about to discuss, you have to be prepared for this shift. Go check out their CISOmarketplace.services program.
Yeah, their methodology is great.
Right. They have developed a 6-pillar AI security department methodology, and it's built specifically to integrate with the advanced architectures we're going to explore today. It is essential reading.
It absolutely is. And, looking at the source materials we're diving into today, the research is pushing the absolute boundaries of machine learning.
We've got a lot of ground to cover.
We really do. We have academic papers detailing the generalizable autonomous pen testing framework, which we'll just refer to as GAP to keep it simple.
AAP, got it.
We're also breaking down Wei Jia's research into swarm intelligence, the Pentest R1 model's two-stage reinforcement learning, and CLAP's coverage-based methods.
It's a heavy stack.
Yeah. And for anyone listening, whether you are a CISO managing a sprawling corporate infrastructure or just a tech enthusiast who is fascinated by the evolution of AI, understanding this stack of research is completely non-negotiable.
It's the blueprint.
Exactly. It reveals the exact mechanisms of how AI explores, understands, and ultimately exploits complex digital systems.
Okay, so let's start by framing the problem we're actually trying to solve here. Because we have human hackers, right?
Right.
They are creative, they are intuitive, they understand the psychology of the people who build these networks. So why are we trying to replace that human intuition with an algorithm? I mean, why do we even need an AI to do penetration testing?
Well, the bottleneck is just human cognition and, honestly, the physics of time.
Time, yeah.
Think about the manual penetration testing cycle you described in your opening. It is deeply time-consuming and incredibly taxing on the human operator.
Because they get tired.
Exactly. A typical enterprise might run an intensive red team assessment annually, or, I don't know, maybe quarterly if they have a massive budget. But the problem is that malicious actors are not operating on a quarterly schedule.
They don't take holidays.
No, they don't. Attackers are currently using automated exploit kits, massive botnets, and increasingly their own AI-driven workflows to continuously probe every internet-facing system on the planet, 24 hours a day, 7 days a week.
So they're essentially turning the internet into a giant radar sweep.
That's a great way to put it.
Like, if you leave a port open for an hour, it gets pinged.
Every single time.
Yeah.
A newly exposed microservice or maybe a database credential accidentally committed to a public GitHub repository.
But that happens all the time.
All the time. Or just a slight misconfiguration in your cloud permissions. These things can be found and exploited dozens of times before your next scheduled manual assessment even begins. So the automated AI pen testing models we are discussing today, They're designed to drastically reduce the time spent on manual vulnerability assessments. They provide a continuous 247 defense posture.
Because they can scale.
Right, they scale across tens of thousands of endpoints simultaneously. A human simply cannot hold the architecture of 10,000 servers in their working memory, but an AI can.
Okay, so the industry recognized this scalability crisis a few years ago, and the logical solution they jumped to was reinforcement learning, or RL.
Yes, standard RL.
Right. The idea was simple, like drop an AI into a network, let it try random things, and give it a digital reward when it successfully hacks a system.
Like a mouse in a maze finding cheese.
Exactly. But according to our sources, those early attempts, things like Nassim, the network attack simulator, or cyber battle sim, they were essentially failures. What went wrong there?
The fundamental flaw in those early models was that their training environments were entirely too abstract.
Too abstract. How so?
They suffered from what researchers call the global perspective assumption.
Global perspective.
Yeah. So when you train a reinforcement learning agent in a simulation like Nassim, the code feeds the AI a perfect top-down map of the entire network topology before the test even begins.
Oh, I see.
Right. The AI instantly knows every host configuration, every open port, every vulnerability.
Okay, I see the problem. That is basically the equivalent of playing a real-time strategy video game with the fog of war cheat turned off.
Exactly.
You can just see the enemy base perfectly from the start, but when a real hacker breaches a perimeter, they don't have a map.
Not at all.
They're blind. They have to grope around in the dark, pinging machines, trying to figure out what they just landed in.
Your video game analogy is spot on. And this reliance on perfect visibility, it created the core dilemma in autonomous pen testing, which the researchers termed the reality gap.
The reality gap.
Right, because when an AI agent trains in a limited, perfectly mapped simulation, it mathematically overfits.
Meaning it just memorizes the answers?
Basically, yes. It memorizes the exact static conditions of that specific simulation to maximize its reward. It learns a hard-coded rule, like to get the reward, I simply look for IP address 192.168.1.0 running Apache version 2.4.
So it's memorizing a script, not actually learning a skill.
Yes. And when you take that overfed agent and deploy it into an unpredictable, real-world enterprise network, the agent completely breaks down.
Because the real world doesn't look like the simulation.
Exactly. Operating systems vary wildly, ports are dynamically assigned, web server fingerprints differ drastically. It encounters a scenario it hasn't memorized, and it freezes. It fails to act.
Wow.
And this reality gap creates what is formerly known as a generalization gap. The skills learned in the lab simply do not transfer to the wild.
This sounds incredibly frustrating from an engineering perspective. I mean, you spend millions of dollars training an AI in a sterile lab, and the second it touches a real corporate network, it trips over its own shoelaces just because the server was running Linux instead of Windows.
It's a massive headache.
Right. So the ultimate question becomes, how do we build a training ground that actually reflects the messy, chaotic, and entirely unpredictable reality of a live enterprise network?
And that is the exact problem the Generalizable Autonomous Pen Testing Framework, or GAP, was built to solve.
Okay, let's dive right into GAP then.
The framework tackles this by completely rethinking the training environment. It introduces the first half of its core architecture, known as the real-to-sim pipeline.
Real-to-sim.
Right. Instead of giving the AI a pre-programmed top-down map, the framework forces the AI to build its own realistic training ground from scratch.
Wait, really? It builds its own simulation. But how does an AI construct a network environment out of thin air?
Well, it doesn't use thin air. It uses raw empirical data gathered through an active OD loop.
ODA loop. Observe, orient, decide, and act.
Exactly. This is the continuous feedback loop the agent uses to interact with an environment. Let's break down the observe phase first. The agent is dropped into an unknown, real, or deeply emulated target network. The researchers often use vulnerable virtual machines like VolHub for this initial stage.
Sure, standard training grounds.
Right. And remember, the agent has no map. So it is forced to use standard real-world cybersecurity tools like Nmap for scanning open ports or Metasploit for executing initial reconnaissance scripts to actively probe the digital environment around it.
Okay, I want to pause right here because this is where the mechanics get fuzzy for me.
Sure.
I have run Nmap scans before. You point it at an IP address, and it spits out walls of raw, messy text data into your terminal.
Oh, yeah, it's very noisy.
It gives you long strings, guessing the operating system, banner grabs from web servers, service versions. It's incredibly chaotic text.
It is.
But a neural network is fundamentally just a massive algebraic equation, right? It only understands numbers. So how does an AI mathematically process all of that chaotic English text?
That translation happens in the orient phase of the loop. To bridge the gap between human-readable text and machine-readable mathematics, the JAP-HE framework utilizes a highly specialized, pre-trained large language model.
An LLM.
Yes, specifically called SentenceBERT. SentenceBERT acts as a mathematical encoder. Its sole job is to take that raw, chaotic text observation from Nmap and compress it into what we call a state vector.
Okay, let's define state vector for the listener who might not have a background in data science. We are essentially talking about an array of numbers, right?
Correct.
But how do those numbers represent something as complex as a vulnerable web server?
Think of a state vector as a set of coordinates in a massively multidimensional space,
Like a map.
like a huge, complex map. Now, SentenceBERT has been trained on millions of sentences. It fundamentally understands the semantic relationship between words.
Okay.
So when it reads the Nmap output, say Apache 2.4.25 running on Ubuntu, it translates the meaning of that phrase into a dense list of numbers, maybe a 768-dimensional array. Yeah. And words or concepts that are functionally similar end up clustered close together in that mathematical space.
That is fascinating. So the AI doesn't actually know what Ubuntu is in a linguistic sense.
Right.
But it knows exactly where it sits mathematically relative to the concept of an operating system.
Precisely. And this encoding process is absolutely vital because it prevents something called a dimensional explosion.
Dimensional explosion? That sounds bad.
It is. If the neural network tried to track every single possible word or character in the Nmap output individually, the mathematical space it would have to calculate would become so astronomically huge that the model would freeze.
It would just crash.
It would require more compute power than exists on Earth. So SentenceBERT condenses the semantic meaning of the network scan into a tight, manageable mathematical vector that the neural network can actually process swiftly.
Okay, that clarifies the observation and orientation immensely. So the AI scans the network, gets a bunch of text, and uses SentenceBERT to turn that text into a tight mathematical coordinate. Now we move to the decide and act phases of the ODA loop. The agent's neural network looks at that coordinate, decides on an optimal next step, and executes an action via an API.
Like firing a specific exploit payload.
Right. But how does it know if it made a good decision? We talked about trial and error, but what are the actual mechanics of the reward system here?
The reward function in the GAP framework is meticulously calibrated, and it's based on subjective expert estimates.
How so?
Well, in older models, the reward was often a simple binary. You get a 1 for hacking the system, a 0 for failing.
Right, win or lose.
But that doesn't work in a complex network. You need granular incentives. In this framework, if the agent successfully exploits a vulnerability and achieves a critical compromise, like gaining root access or popping a shell,
It gets the jackpot.
it does. It receives a massive reward of plus 1,000.
The ultimate dopamine hit for the algorithm.
Exactly. But, getting to that jackpot requires hundreds of smaller steps. So the framework provides incremental rewards to encourage good behavior along the way.
Like what?
The agent gets a plus 100 reward for gathering vital, actionable information during reconnaissance.
Oh, interesting.
Yeah. If it successfully identifies the exact OS type or correctly maps the running services on a port, it gets paid. It is being explicitly rewarded for being a thorough detective.
I love that. But what happens when it makes a mistake? If it fires a Windows exploit at a Linux server, does it get punished?
It does, but the penalty is carefully tuned. It receives a -10 penalty for taking illogical, invalid, or impossible actions.
Wait, only -10.
Yeah, just -10.
I mean, if the jackpot is 1,000, a 10-point penalty seems like a slap on the wrist. Why not punish it severely, say -500, to really teach it not to fail?
Because if you make the penalty too severe, you trigger a known problem in reinforcement learning called reward sparsity paralysis.
Paralysis.
Right. The agent becomes mathematically terrified of making a mistake, so it stops exploring altogether.
It just sits there doing nothing to avoid the massive penalty.
Exactly. You want the agent to try new things. However, you still need that -10 penalty to instill a sense of operational stealth and efficiency.
Because you can't just be noisy in a real network.
Right. In a live enterprise environment, firing off random, illogical exploits at every open port generates a massive amount of network noise.
Hmm.
A Human Security Operations Center, a SOC, will detect that anomaly instantly and shut the connection down.
Yeah, you trigger every alarm in the building.
So the -10 penalty slowly trains the agent to be purposeful, quiet, and deliberate with its actions.
That makes perfect sense. It is a balancing act between encouraging curiosity and demanding precision. So, the agent cycles through this ODA loop thousands of times. It scans and codes with sentence BERT, acts and gets its points docked or rewarded.
Yes.
But the final output of this entire reel-to-sim phase isn't just a smarter AI, right? The crucial byproduct of all this scanning is the simulation itself.
That's the key. The agent takes all the configuration data it just gathered, the ports, the OS, the services, and automatically constructs a highly realistic digital replica of the target network.
And it builds this entirely in JSON format, right?
It literally maps the specific environment it just traversed and saves the entire topology as a structured JSON file.
And a JSON file, for context, is essentially just a nested dictionary of key value pairs used to store data logically.
Exactly. It creates a digital twin of the target.
Okay, but here is the massive logic gap I am seeing with this.
What's that?
If the agent just spent hours building a perfect JSON replica of the one specific network it scanned, aren't we right back to square one?
I see what you're saying.
I mean, it has successfully mapped one specific room. If I take that agent and deploy it into a completely different corporate network tomorrow, it's going to fail.
Because it overfit to that single JSON file.
Exactly. How do we get from one isolated simulation to an agent that can generalize across the entire internet?
You have identified the exact bottleneck that has plagued the industry for years. And it is the precise reason the framework moves into phase 2, which is the sim-to-real pipeline.
Sim-to-real.
Right. To prevent the agent from overfitting to that single static JSON replica, the researchers introduce a technique borrowed heavily from the robotics industry.
Which is?
Domain randomization. And they supercharge this randomization by integrating a generative large language model.
Domain randomization via an LLM.
Okay, let's unpack the mechanics of this. How exactly does an LLM randomize a network topology?
In the JP framework, the researchers utilize a powerful generative AI, specifically the GLM-4 model, to artificially augment the training data. The process is incredibly elegant.
Walk me through it.
The system feeds the LLM two distinct pieces of context. First, it inputs the baseline JSON simulation the agent just created, the exact real-world replica of the target network.
Okay, that's step one.
Second, and this is the critical step, it feeds the LLM the official, standardized vulnerability descriptions pulled directly from the National Vulnerability Database. The NVD.
Yes.
For those outside the security bubble, the NVD is effectively the global master dictionary of every known software flaw. It documents what the flaw is, how it works, and what software versions are vulnerable.
Exactly. The NVD provides the foundational mechanics of the exploit. So the LLM takes the baseline JSON file, processes the NVD context, and is prompted to synthesize dozens or even hundreds of new, completely synthetic JSON variants of that original environment.
Give me a tangible example of this. Paint a picture for the listener of what this JSON randomization actually looks like under the hood.
Let's look at a very famous vulnerability, CVE 2018-7600.
Ah, Drupalgeddon.
Yes, Drupalgeddon. It was a catastrophic flaw in the Drupal content management system that allowed attackers to execute arbitrary code remotely.
Oh, nightmare.
Yeah. So let's imagine our AI agent scanned a training server, and the baseline JSON replica build shows that the vulnerable Drupal application is running on standard port 8080.
Okay.
The JSON also notes that the underlying operating system is Linux kernel version 4.15, and the web server is Apache version 2.4.25.
So the AI has a very specific, narrow picture of what a vulnerable Drupal server looks like.
Yes. Now, the GLM-4 model goes to work. It reads the JSON, reads the NVD file for Drupalgeddon, and generates a synthetic variant.
And what does that variant look like?
In this new JSON file, the LLM moves the Drupal application to an obscure port, like 9000. It alters the Apache web server to a newer version, maybe 2.4.26. It changes the operating system from Linux to a specific distribution of Debian.
Wow, so it's a completely different disguise.
And it might even sprinkle in 3 or 4 randomly open ports running fake FTP or SSH services just to create background noise.
But the risk here is, well, if the LLM changes too much, it might accidentally patch the vulnerability.
True.
If it changes the Drupal version itself to a patched version, the exploit won't work and the training environment is ruined, right?
And that is the brilliance of feeding it the NVD context.
Oh, because it knows the rules.
Exactly. The LLM understands the semantic boundaries of what it is allowed to change. It knows it can alter all the superficial disguises, the ports, the OS, the background services,
Right.
but it mathematically ensures that the core vulnerability remains functionally exploitable within the synthetic JSON. It maintains semantic coherence while randomizing the external presentation.
I love this concept. Let's put this in human terms. Imagine you are training a detective to spot a specific counterfeiter in a crowd.
Okay.
First, you show the detective a photo of the suspect wearing a red jacket. If that is the only training data you provide, the detective will go into the field and only arrest people wearing red jackets.
They overfit to the clothing.
Exactly, they overfit to the clothing. But domain randomization uses the LLM to generate 1,000 synthetic photos of that same suspect. Now the suspect is wearing a blue jacket, now they have sunglasses, now they're wearing a hat, now they are standing in the rain.
And by forcing the detective to process all these variations,
They stop looking at the clothes. They learn to recognize the underlying bone structure of the suspect's face.
that is a phenomenal analogy. The AI agent stops looking for port 8080 and starts recognizing the underlying algorithmic structure of a memory leak or an injection flaw.
It learns the essence of the vulnerability.
Yes, and I want to emphasize something crucial for the security practitioners listening right now.
Go ahead.
This is not theoretical academic vaporware. Security teams can implement these exact domain randomization steps in their own labs today.
Today.
Yes, the GIP source code, including the specific prompt engineering used to force the LLM to generate these JSON variants without breaking the exploits, is publicly available on GitHub.
That is
We
amazing.
can pull that repository down this afternoon and start building dynamically diverse training data sets for your own internal models.
That is huge. And if we take a step back and extrapolate where the broader cybersecurity landscape is heading, this technology isn't just a neat trick, it is an absolute necessity.
Why do you say that?
Because malicious AI-driven cyber threats are evolving, and they are going to start using these exact same generative techniques offensively, right?
Oh, without a doubt.
A sophisticated malicious AI isn't going to just sit on a static IP address using a recognizable payload. It is going to dynamically shift its own network configurations, constantly altering its digital fingerprints to evade detection.
The offensive malware of tomorrow will be a shapeshifter.
Exactly.
And this domain randomization training is the exact countermeasure defensive AI will use to adapt. By forcing our defensive pen testing agents to train against thousands of LLM hallucinated variations, we are pre-training them to recognize the foundational mechanics of an attack.
Regardless of whatever superficial dynamic disguise the malicious AI attempts to wear.
Exactly. We are actively inoculating enterprise defenses against dynamic AI-driven offenses.
Okay, so the logic is sound. We use the real-to-sim pipeline to build a baseline, and we use LLM domain randomization to spawn thousands of synthetic variations of our network. But as I think about the computational reality of this, a massive problem emerges.
Compute cost.
Yes.
Yeah.
If we force a single AI agent to train on thousands of different network topologies, isn't that going to take years of compute time? Standard reinforcement learning is notoriously slow. How does the agent process all this synthetic diversity without the training time becoming astronomically expensive?
If the researchers relied on standard reinforcement learning, it would indeed take forever. The compute cost would be completely unviable for a commercial enterprise.
Right.
The GAP framework bypasses this limitation entirely by utilizing a much more sophisticated mathematical approach called meta-reinforcement learning, or meta-RL.
Meta-RL, the concept of learning to learn. Let's dig deep into this, because this is where the AI stops acting like a calculator and starts acting like a cognitive entity.
It is a massive shift.
Yeah.
In standard RL, the agent is essentially trying to memorize the optimal sequence of steps to reach a reward. It learns what to do. In meta-RL, the goal shifts completely. The agent is no longer trying to memorize specific attack paths. Instead, by experiencing this massive, diverse distribution of randomized tasks, the neural network extracts what machine learning researchers call inductive biases.
Let's define inductive biases clearly for the listener. What does that actually mean in the context of a neural network?
An inductive bias is essentially a set of mathematical assumptions or generalizable strategies that a learning algorithm develops to predict outcomes for situations it has never explicitly encountered before.
So in human terms, it is intuition.
Exactly. It's intuition. It is the underlying framework of problem solving. Instead of memorizing what to do in a specific network, the agent learns how to figure out what to do in any network.
It's the difference between memorizing a specific recipe to bake a chocolate cake versus learning the fundamental chemistry of how flour, sugar, and heat interact.
Yes.
Once you understand the chemistry, the inductive bias, you can walk into any kitchen in the world, look at whatever random ingredients they have, and figure out how to bake something edible.
That's a perfect way to look at it. Now, the research we are analyzing compares two distinct mathematical approaches to achieving this meta-RL state:
What are they?
recurrence-based methods and gradient-based methods. It's important to understand why they chose the latter.
Okay, let's break them down.
Recurrence-based methods, like the RL2 algorithm, rely heavily on recurrent neural networks, or RNNs. These models attempt to handle new environments by feeding the agent a massive, continuous stream of its own historical experiences.
So to use the kitchen analogy, it's like a chef trying to invent a new dish by constantly flipping through a diary of every single meal they've ever cooked in their entire life.
Exactly. It works, but it requires a massive amount of memory, and scanning that memory bank is computationally sluggish.
So what does the GAP framework use instead to speed things up?
It abandons the memory-heavy approach and uses a gradient-based method. Specifically, it employs an algorithm called model-agnostic meta-learning, or MAML.
Model-agnostic meta-learning, MMLL, how does that change the math?
MML is vastly superior in this specific cybersecurity context because it offers incredible parameter efficiency and rapid adaptation.
Because it isn't scanning a diary.
Right. It doesn't rely on hauling around a massive memory bank of past experiences. Instead, MML is focused entirely on optimizing the agent's initial neural network parameters. It tunes the starting line.
Let's break down how MML actually tunes those parameters, because our sources describe it as a very specific two-loop learning structure. What happens in the inner loop?
The inner loop is focused exclusively on task adaptation. Imagine the agent is dropped into just one of those synthetic JSON environments. Let's say it's the Drupal vulnerability running on port 9000 with the Debian OS.
Okay.
The agent interacts with this specific environment. It tries out different actions using a standard policy gradient algorithm, which is just a mathematical way of tweaking its behavior to get more points.
Right.
As it learns to hack this specific Debian environment, it generates something called a metagradient.
A metagradient. I know what a standard gradient is in machine learning. It basically measures how far off your prediction was, so the algorithm knows which direction to adjust its weights.
Right.
What makes a gradient meta? What is it actually measuring?
A standard gradient measures error on a specific task. A metagradient calculates how the agent's performance on this specific new task affects the necessary updates to its overall foundational policy parameters.
Okay, I think I'm following.
It isn't just measuring the error, it is measuring the rate and trajectory of the learning process itself. It asks, how much did my core intuition need to shift to solve this puzzle?
Okay, so the inner loop runs, the agent hacks the Debian environment, and it outputs a metagradient that says, here is how my intuition shifted.
Yes.
What happens in the outer loop?
The outer loop is the meta-training phase. The system doesn't just look at one environment, it collects these metagradients across multiple, completely different tasks simultaneously.
Oh, wow.
It takes the metagradient from the Debian on port 9000 maze. It takes the metagradient from the Apache on port 80 maze. It takes the metagradient from the noisy FTP maze.
And it aggregates them.
Yes. It aggregates all of these metagradients, mathematically averages out the overarching lessons, and uses that data to profoundly update the agent's initial neural network parameters.
And this right here is the absolute aha moment of the entire framework.
It really is.
By continuously running these two loops and updating the initial parameters, the agent develops an incredibly optimized starting point.
Exactly.
When you finally take this agent out of the lab and deploy it into a brand new, unseen enterprise network in the real world, it doesn't start with a blank slate. It doesn't start from zero.
No, it starts from a state of highly tuned, generalized readiness. It starts with that baked-in intuition we discussed.
Like a master key.
Think of it exactly like a master skeleton key.
Yeah.
It might not perfectly fit the lock on the very first try, but the grooves are cut so precisely that it only takes a micromillimeter of filing, just a few tiny gradient steps, for it to click open.
Wow.
It requires almost zero computational retraining to succeed in a totally novel environment.
This transition from the lab to the real world brings us perfectly into the deployment phase.
The real test.
Right. The agent has survived the real to sim to real pipeline. It scanned a baseline network, built a JSON replica, the LLM randomized it into 1,000 variants, and MEMML baked in the inductive biases.
Yes.
Now, a CISO takes this agent and drops it into their live corporate network. What happens next depends entirely on how the new environment compares to its training data. Let's look at how the agent differentiates its approach. Our sources talk about zero-shot policy transfer. What does that actually mean in practice?
Zero-shot policy transfer occurs when the deployed agent encounters what the researchers define as a similar environment. Now, it is critical to understand that similar does not mean identical.
Right, the LLM made sure of that.
Exactly. These external host configurations, the operating systems, the assigned ports, the web server fingerprints, they might be completely mismatched from anything the agent saw on the baseline network.
So the disguise is completely new.
Yes. But, crucially, the environment contains a vulnerability whose underlying mechanics the agent has encountered before during its meta-training.
The bone structure is the same.
Yes. Because of the LLM domain randomization we discussed, the agent looks past the mismatched OS and the weird ports, and it recognizes the mathematical signature of the vulnerability itself. It bridges the generalization gap instantaneously.
Meaning it compromises the target on the very first try?
Yes, it executes the correct sequence of actions instantly, without needing any prior interaction, trial and error, or retraining within that specific network.
That is why it is called zero-shot.
Zero retries. Zero learning curve. The intuition takes over completely.
That is staggering. To have an AI drop into a totally unfamiliar subnet and instantly pop a shell because it recognizes the underlying architecture of a flaw.
It's incredibly powerful.
But let's look at the harder scenario. What if the agent drops into a network and encounters a completely novel vulnerability, something it has never seen in its NVD training data?
That constitutes a dissimilar environment. In this scenario, zero-shot transfer is impossible. The agent doesn't have the specific intuition for that exact flaw.
So it has to learn.
However, this is where MML truly shines. The agent transitions into few-shot policy adaptation. Because it has developed those profound inductive biases, because it fundamentally knows how to process network feedback, it begins interacting online with the environment.
Trial and error.
It probes, it acts, it observes the outcome. But instead of taking thousands of attempts to learn, it rapidly adjusts its policy to exploit the new target in just a limited number of shots. It figures out the new puzzle incredibly fast.
And we don't just have to take the researcher's word for this. We have the hard empirical data from the GAP framework benchmark testing to prove just how revolutionary this jumpstart performance is. The math here is undeniable. Let's look at the correlation statistics.
The numbers validate the entire architecture. Your researchers track the agent's initial jumpstart performance, how well it did on its very first few shots, and map that against the total time required to fully learn the new environment.
And what did they find?
They found an incredibly strong negative linear correlation.
We are talking about a Pearson's R coefficient of -0.99.
That's massive.
For anyone listening who hasn't taken a statistics class recently, a Pearson's R of -1 represents a perfect, mathematically absolute negative correlation. A score of -0.99 means it is an almost irrefutable certainty that as the agent's initial intuition, its jumpstart performance increases, the computational time it takes to conquer a new environment plummets.
It's practically a one-to-one relationship. When you look at the real-world time savings, the GAP transfer method reduced the average training time required to compromise a novel target by 40% compared to a standard RL agent learning from scratch.
40%.
In their specific benchmarks, the time dropped from over 4,000 seconds to roughly 2,400 seconds.
So let's ground this for the listener. Imagine you are a CISO. You are looking at your security budget, your risk exposure, and a sprawling, highly diverse corporate network that spans 3 continents, multiple cloud providers, and thousands of endpoints.
A huge attack surface.
What is the practical bottom line benefit of deploying an autonomous framework like this?
The practical benefit comes down to unparalleled consistency and the absolute eradication of assessment fatigue.
Fatigue again?
Right. Human security teams, no matter how elite they are, suffer from cognitive fatigue.
Yeah.
If you instruct a human analyst to manually check 10,000 diverse, slightly mismatched endpoints for a complex multi-stage vulnerability chain, they will inevitably miss things.
Of course they will. They're human.
An agent trained with a GAP framework never gets tired. It handles highly diverse, sprawling configurations with mathematical precision. It allows an enterprise to have a highly skilled, constantly adapting AI actively probing its perimeter 24/7, identifying and validating risks before malicious actors do.
And executing this with a level of computational efficiency that was literally impossible 5 years ago.
Exactly.
Okay, the GAT framework proves that a single, highly trained AI agent can generalize, adapt to mismatched configurations, and dramatically reduce assessment time. That alone is a massive leap forward.
It is.
But let's look at the reality of modern infrastructure. Enterprise networks are not just a handful of servers. They are enormous, labyrinthine architectures featuring containerized microservices, legacy mainframes, IoT devices, and complex Active Directory forests.
The chaos.
A single agent, no matter how much MML intuition it has, is going to get bogged down trying to map 100,000 nodes. How does this autonomous framework evolve to actually support real-world, large-scale enterprise security?
That is the crucial next frontier, and our stack of sources dives deeply into this evolution. To scale from a single server to an enterprise forest, the architecture must move from single isolated agents to what we call cognitive swarms.
Swarms. I love this part.
We're looking at decentralized, multi-agent frameworks, specifically highlighted in the research surrounding YGA and PentAGI. These frameworks abandon centralized control entirely and utilize something called stigmergic coordination.
Stigmergy. That is a concept pulled straight out of biology, isn't it? It describes how social insects like ants or termites manage to build massive, complex structures without having a blueprint.
It is exactly that. If you watch an ant colony forage for food or build a nest, there is no CEO ant standing on a leaf shouting orders.
Right.
There is no central orchestrator running a master script. Instead, the ants coordinate their actions indirectly by modifying their shared environment, specifically by leaving chemical pheromone trails.
Okay.
If an ant finds a food source, it leaves a trail. Other ants stumble upon the trail, follow it, and reinforce it with their own pheromones. The environment itself becomes the communication medium.
So how do you translate biological pheromones into code for AI hackers? I mean, how do they communicate without a central boss telling them what to do?
In a swarm framework like YGA, you eliminate the central planner entirely. Central planners in AI often get stuck in infinite computational loops trying to sequence a million possible tasks.
You just get overwhelmed.
Yes. Instead, YGA deploys a multitude of highly specialized independent agents. You have a dedicated reconnaissance agent, a specialized exploitation agent, a lateral movement agent, a privilege escalation agent.
So a whole team.
Right. They all operate autonomously, but they coordinate indirectly by reading and writing their findings to a shared central database.
What kind of database?
Typically a PostgreSQL-backed database, which the researchers refer to as the blackboard.
And the data they write to this PostgreSQL blackboard acts as the digital pheromones.
Yes. Every piece of data written to the blackboard is assigned a pheromone weight based on its potential value. Let's trace a scenario.
Walk me through it.
The reconnaissance agent is scanning a massive subnet. It finds an obscure open port that looks vulnerable. It drops a JSON note onto the blackboard detailing this finding and assigns it a high pheromone weight. It doesn't tell anyone what to do with it. It just leaves the note.
But the other agents are constantly sniffing the blackboard.
Exactly. The exploitation agent, which has been dormant, wakes up because it detects a high weight finding on the blackboard. It reads the note, navigates to the port, and attacks it.
Wow.
If the attack succeeds, the exploitation agent extracts a hashed password. It drops that password back onto the blackboard with an even higher pheromone weight.
And then the next agent wakes up.
That organic action wakes up the privilege escalation agent, who grabs the hash and tries to crack it to gain root access.
It is an incredibly beautiful, decentralized cascade of actions. And the most profound aspect of this stigmergic coordination is that because these agents are not following a rigid human-programmed playbook, because they are just reacting organically to weights on a blackboard, they uncover vulnerabilities that human engineers would never even conceive of.
They surprise us constantly.
I want to highlight an astonishing data point from the YAGA benchmark testing. During their evaluations against complex networks, 17% of the successful attack chains generated by the swarm were completely unanticipated.
17%.
They were novel attack paths that were not written in any predefined security playbook. The swarm organically chained together tiny, seemingly unrelated misconfigurations to achieve a critical breach, finding blind spots that human defenders simply didn't know existed.
That emergent behavior is the true, terrifying power of swarm intelligence. It is the ultimate defense strategy because it assumes nothing. However, engineering this swarm introduces a massive mathematical challenge.
What is that?
It's known as the sparse reward problem.
Sparse rewards, meaning they don't get paid often enough.
Exactly. In a massive enterprise network with 100,000 endpoints, a reconnaissance agent might need to take thousands of actions, pinging dead IPs, scanning closed ports, before it finally uncovers something valuable enough to get a reward.
Right, it's a needle in a haystack.
If an RL agent goes too long without a reward, the mathematical gradients flatten out. The agent essentially gets bored, gets lost, and stops learning.
So if the actual rewards are too spread out, how do you keep the swarm motivated to keep searching the dark corners of the network?
You have to engineer motivation.
Yeah.
In the YGA framework, they solve the sparse reward problem by implementing a curiosity engine.
A curiosity engine.
They achieve this by combining a reinforcement learning algorithm called proximal policy optimization, or PPO, with a technique called random network distillation, or RND.
Random network distillation. Okay, let's break down the math of how you actually code curiosity into a machine.
RND is an incredibly clever workaround. It utilizes two separate neural networks running in parallel.
Okay, two networks.
The first is a fixed, randomized network that takes in data about the environment and outputs a deterministic mathematical embedding. Its weights never change.
Right.
The second is a trainable predictor network. The predictor network's entire job is to look at the environment and try to guess exactly what the fixed network is going to output.
Okay, I am following. One network creates a random baseline, the other tries to predict it. How does that create curiosity?
If the AI agent is wandering around a part of the network it has seen 100 times, say a standard cluster of Windows workstations, the predictor network becomes very good at guessing the output. The prediction error is near zero.
It's familiar territory.
But if the agent wanders into a novel, unseen adversarial state, perhaps a weird, undocumented legacy mainframe subnet it has never scanned before, the predictor network will fail completely.
Because it has no idea what it's looking at.
Right. It can't guess the output because it has never seen this data. The mathematical error rate spikes massively.
And the system takes that high error rate
and turns it into a reward. The system takes that high prediction error and feeds it directly to the agent as an intrinsic curiosity bonus.
That is incredible.
It literally gives the AI points just for exploring somewhere new and confusing, even if it hasn't actually found a vulnerability yet.
That is absolutely brilliant. It mathematically rewards the behavior of exploration itself to bridge the long, boring gaps between finding actual vulnerabilities.
Okay, so we now have a highly curious, relentless swarm of AI agents sharing information organically on a PostgreSQL blackboard, chaining together novel attacks across tens of thousands of endpoints.
Yes, a formidable force.
But as we apply this to the real world, an enormous, terrifying concern becomes glaringly obvious.
The operational safety of the live network.
Exactly. Let's say you point this highly curious autonomous swarm at the live network of a major metropolitan hospital.
High stakes.
The swarm finds a deeply hidden vulnerability in a database and decides to test a memory corruption payload. If that payload is unstable, if the math is slightly off, it won't just fail, it will crash the server.
Absolutely.
It could cause a massive denial of service outage, taking down patient records, telemetry, critical healthcare infrastructure. How do we allow these swarms to rigorously test their emergent exploits without risking the operational stability of the enterprise? It is the most critical question regarding actual deployment, and our sources address it directly. The solution lies in a concept called conditional isomorphic validation, which is executed using highly advanced digital twins.
Digital twins.
Yes. Frameworks like Automation Exploit are built around this safety mechanism. When an agent in the swarm discovers a potential vulnerability and generates a payload, it is strictly forbidden from firing that destructive payload at the live physical target.
So what is the validation sequence? Where does it fire it?
The sequence begins with exfiltration. The agent carefully extracts the target binary or the specific vulnerable service code out of the live environment.
Okay.
It then dynamically spins up a completely isolated cross-platform digital twin of that exact target environment within a secure sandbox.
A sandbox replica. But we established earlier that if the replica isn't perfect, the exploit might work in the sandbox but fail in the real world. How do they ensure the twin is identical?
They perform deep state synchronization. It goes far beyond just matching the operating system. For complex memory corruption exploits, the memory addressing must be flawless.
Right, because of memory layout.
Modern systems use address space layout randomization, or ASLR, to shuffle memory around. So the agents must strictly align the foundational libraries. For example, they meticulously synchronize the GNU-C library, the limerick, between the live target and the digital twin.
Wow, that deep.
Yes, this ensures that the mathematical memory pointers in the sandbox perfectly match the memory layout of the real server.
That level of synchronization is incredibly intricate. But once the lib and the memory states are aligned, what happens?
Once the digital twin is perfectly synced, the agents can iteratively unleash their payloads inside the safe sandbox. They can debug the code, trigger memory leaks, and crash the sandbox server 1,000 times without risking a single millisecond of downtime on the actual hospital network.
They practice the shot in the simulator.
Exactly. Until the exploit logic is absolutely perfect. Only once the exploit is mathematically proven to be stable, effective, and non-destructive within the digital twin does the system authorize the delivery of a highly reliable, risk-mitigated, one-shot execution payload to the live physical target.
They know it will work, and they know it won't crash the system because they already tested it in a parallel universe.
Precisely.
This sounds like science fiction, but as we conclude our analysis of these sources, it is vital to understand that this is transitioning into reality right now. The research points toward a near future dominated by hybrid human-AI operations. Leading penetration testing as a service platforms, P-test platforms like Synac, HackerOne, and others are actively studying and beginning to deploy these exact types of AI agents.
The division of labor is fundamentally shifting. They are utilizing AI swarms for the initial, massive-scale vulnerability triage and continuous surface exploration.
Then grunt work.
Right. The AI swarm does the exhausting heavy lifting. The 247 scanning, the domain randomization, the emergent attack chain discovery via the blackboard. And when the swarm conclusively validates a complex vulnerability in a digital twin, it packages that proof of concept and passes it up the chain to an elite human researcher.
So humans are still in the loop.
Yes. The human steps in to review the broader business context, sign off on the actual risk severity, and work directly with the enterprise engineering teams to remediate the flaw. It represents the perfect, scalable marriage of relentless machine computation and nuanced human judgment.
What an absolute marathon of an exploration we've been on today. We started with the fundamental problem of human scalability and the reality gap of early models. We explored how the real-to-sim pipeline allows agents to drop into an unknown network, actively scan it with OODA loops, and use SentenceBERT to compress chaotic text into actionable mathematical state vectors.
We examined how those scans generate baseline JSON replicas and how generative models like GLM-4 execute domain randomization, hallucinating thousands of diverse synthetic environments while using MVD data to preserve the core exploit mechanics.
We took a deep dive into the calculus of MML meta-reinforcement learning, discovering how the two-loop structure allows the agent to extract inductive biases, learning how to learn, resulting in astonishing zero-shot policy transfer against mismatched configurations and vastly reducing training time.
And finally, we scaled this massive architecture to the enterprise level, detailing how stigmergic swarms coordinate via pheromone weights on a PostgreSQL blackboard, driven by the PPO and R&D curiosity engines, safely validating the organic attack chains within synchronized live digital twins.
It fundamentally rewrites the rules of digital defense. But I want to leave you, the listener, with a final thought to mull over, a concept that extends slightly beyond the immediate research, but is the inevitable, chilling conclusion of this technology. We have spent this entire deep dive discussing how AI swarms are learning to explore, adapt, and hack static enterprise networks to defend us. We are building incredibly intelligent, curious, autonomous missiles to hit static targets. But what happens when the enterprise networks themselves become fully autonomous?
The architecture of the battlefield changes entirely.
Imagine a future enterprise infrastructure that doesn't just passively sit there waiting to be scanned. Imagine a network powered by its own defensive AI that detects the subtle, stigmergic probing of an incoming autonomous pen-testing swarm. Instead of just blocking the IP addresses, which we know the AI will just route around, the defensive network dynamically hallucinates 1,000 fake, perfectly vulnerable digital twin environments in real time. It actively reshapes its own JSON topology, trapping the attacking AI swarm in a constantly shifting labyrinth of its own making, feeding the swarm endless curiosity rewards for exploring dead-end synthetic subnets. We started this discussion talking about the challenge of finding vulnerabilities in a static system. The future we are accelerating toward isn't just AI swarms finding flaws faster than human analysts. The future is an ecosystem of defensive AI swarms fighting offensive AI swarms, mutating and adapting their network topologies by the millisecond, engaging in a silent mathematical cyber war in an ocean of data we can't even perceive.
A truly autonomous, self-modifying battleground.
It is a profound shift in the nature of security. I want to give one final massive thank you to our sponsors, CISOmarketplace.com. If you want to prepare your infrastructure for this autonomous future, please explore their CISOmarketplace.services program and dive into their 6-pillar AI security department methodology. It will give you the foundational tools you need. Until next time, keep questioning the systems around you, keep looking at the underlying mechanics, and we will see you on the next deep dive.